Okay, exabyte. When you hear the word exa, you already start thinking about big things. And I will talk about a lot of big things, a lot of data. But first, the question, who needs exabyte of data? So there are several candidates here. I promise our system will not work for the last one. The other four can come afterwards to talk to me. You ask the question. I mean, probably some of you know that a small company. We are fitting all together in a balcony, an old house. So why a small company like mine are trying to build systems like Amazon and other big guys? And are we insane? The short answer is yes. But there is also a longish answer. And the longish answer is all our lives we spent with a lot of data, working with a lot of data, different types of data, and so on. So this is the only thing that we actually. So I will start with a little bit history. We started building large databases or based on data system already at 1978, where we had to bring the data in a punch cards, in the big boxes of 2,000 punch cards. And we had many different projects in our company with my colleagues, my friends. Some examples: large biochemical and biological databases like DNA, protein structures, RNA, and so on. Something that we did here, very close to London, in Poole, actually, is helped to make the image archive for the Mars rover mission. And that was fun. We understood that actually NASA have also a big problem with lots of data, and they don't know how to solve it properly. We worked on different systems for hospital systems, for biolabs, and so on. A lot of the first really fun project for me was when we were building one of the first in the world robotic observatory control system. And this is with telescopes to 3 continents: North America, Africa, and in Europe. For the last probably 20 years, we're building for the Dutch market a very large transactional database between large banks and the government. And yesterday in the pub, I've heard that actually some of you here, Brits, prefer this cat to be the prime minister than the current prime minister. And finally, our new pet project, this is SpaceJunk, a database for SpaceJunk that surrounds the world. And this is the project that actually pushed us to build this new version of our data archive. And this is actually the third version of our data archive. The first one we started at the end of the 90s for a company called Henkel, CEO and Schwarzkopf. And we built a very large data archive for their data warehouse. Then later, for this Monet project the astronomy project, we built our second archive, second version of our archive. And it was with, afterwards we used it in German government projects like the German police for Baden-Württemberg or education ministry for the province of Lower Saxony. So exabyte, it's a lot of data. I will make a short visualization how much it is. So some of you remember this one, very few of you remember this one. This is a ferrite memory that contains 128 bytes. And many of these ferrite memories fit in one Mac write diskette, 3-inch diskette. Some of you remember also this. Many of these diskettes fit in one Next Cube that was coming in the standard configuration of 260 megabyte. Imagine. Then many cubes were fitting in one Power Mac G4. And many G4s were fitting in the combination of Studio and Mac Mini. And not so many of them are making 1 petabyte. And a lot of them make 1 exabyte. So this is the amount of data that we're talking. So a lot of data. So the question is, what are our goals? Before you have to set some goals and how to design them. And the first of our goal is actually absolute privacy. We do not want to deal with 3-letter agencies. We do not want to put canary, coal mine, white papers, or then remove it from our website. This should be absolutely protected, and we do not have the key. The second one is configurable. Every data piece should have read, write access, share to organizations, to user groups, to individuals, and so on. Then it comes the separation by continent. For instance, NASA would like to have all the data in US. ESA would like to have all the data in Europe, and so on. So we need this separation. Very important for here, for this conference, are the APIs. So obviously we have a Swift API. We have REST APIs and web interface. And the APIs should be stable and well designed. Something that is very important also is bitrot. I mean, you probably know that we are sitting here in this beautiful hall, and there are all kinds of cosmic rays hitting our computers and flipping some bits. And after a couple of years, you will see that in 1 gigabyte, you have at least 15 files that are not anymore the same as you put them there. So our system should actually protect from bitrot. And then should also be resistant to other type of failures, hardware failures. And here I bring this mouse here because actually this summer I had a Greek mouse that actually managed to almost destroy my new Volvo. So if a Greek mouse can destroy a car, obviously can destroy also computers and servers. We need backups, obviously, for the data. And as I told, this data should be regionally stored. We need versioning. So basically we need unlimited amount of versioning. And we need a disaster recovery. And disaster recovery, I will mention it a little bit later, but I mean, we really, if we want to host data for space agency, I mean, if the entire data center goes dark, we have to recover somehow. These are the requirements. The data could be stored either as an entire file or in chunks. And these chunks, of course, the files and the chunks have to have checksums so that we constantly can prove that the data is still okay. If it's not okay, to repair it. And very important, around the data, about the entire files, around the chunks, we have also metadata. And there are layers of metadata. We call them a data onion. And the first one, the default one, keeps stuff like the type of the file, the size of the file, different IDs, and so on and so on. And then you have other layers around the onion that are, for instance, key value layer. We are providing our API provided directly to you. And then you can also add to your own files data. You can add your own metadata around it. This is very important to analyze the data later. So, and we have also to basically have the data predictable, to have the access to the data with predictable speed. So we want to avoid stuff like Java kicks up the garbage collector or MongoDB start reorganizing or whatever. It's not acceptable. So I actually rewrote my talk 3 times, because first time it was too technical. The second time I thought, okay, I will tell about different design patterns, but then I lost the red line. And the third line, I thought, I mean, I cannot tell everything about such a huge system. So I was in one of these stupid meetings that take forever, and you have a project manager that tells you, well, you cannot run the stuff on an Apple machine. And what is this language Swift? Come on, be serious. So I thought, okay, one thing that I would like you to take with you when I finish is that actually you can develop such a huge system on Apple machines with Swift language. So I will give here hints how we implemented this one. No source code. I mean, if you like, later on you can talk to me about some technical implementation and so on. But basically the takeaway should be how we did this one, the principle of how we did this one. And that actually that you should be courageous enough to do it the same. So the first thing, implementing the privacy. Very simple. You encrypt the disk. And why you encrypt the disk? Because in the data center, somebody can come and take your disks and then the data are gone. Encryption, the disks have positive sides, obviously, and that is safe. But the negative side is that when you reboot the server, you have to type the password. So we have an implementation how to avoid this retyping the password and so on. But if somebody knows actually a better way, I will be very happy to hear it. You remember this icon? There was no liquid glass. So the question is how we store an object. Imagine you want to log in and submit, say, large file to the system, how it looks like. So you have a custom login, and you give your authentication and so on. And we return you a transaction ID. And this transaction ID is important because you can always come back to us and say, what happened with this transaction? I mean, if you're uploading 10 gigabyte file, obviously this will be not immediate. So you might later want to ask what happened with it. So next, you set your permissions. So who has the right to this data? Is it a group? Can the other people write to it or not? And so on and so on. You can also commit your metadata if you have additional metadata. And then you can stream the file. When the file is streamed, we make an initial checksum, and we give you this checksum so that you can check also on your side if it's the same. Then we're moving the data to a data node, calculating different things like checksums and so on and so on, and preparing the data onion and then the data is done. Then the next step is we multiply the data. By default, we multiply it 3 times, so 2 different clusters in 2 different geographical locations, on 3 different servers and 3 different disks. This is the default, and you can configure it, obviously. We check, again, the checksums, that all 3 places have the checksums of the same. And then, basically, the transaction is done. And when it's done, we're giving you access token. With this access token, you can later retrieve the data. And we also make a transaction log. This is a requirement. Most governments require the transaction. And we can send you also notification that the transaction is okay or failed and so on. And we produce the data onion at the end. And data onion is very important because you can imagine that, for instance, astronomical data. You submit an astronomical image, and then you start munching on it and say, okay, is it an X-ray image? Is it where it is? Where is it in the sky? Is it something interesting? Can I find a supernova there? And so on, this type of. So this is, and we have a default crawlers, data crawlers, and you can, if you use our APIs, you can also submit a crawler, and you can do your task. And these data onions, they could be also encrypted. We don't have to know what data you're putting. So internally, the access to the file looks like a URL. And here is how this URL, a little bit bigger, and how it's built. So we have the server, the data node, and we have the volume ID. We have the ID of the file, and we have a random ID. By the way, in our previous versions, we had the UUIDs, and try to put UUIDs in a binary. It's a better. So we were young and stupid at that. Now we have IDs that you can index properly, but then you have to have it so that no one can guess these numbers. So we add also a random ID. And then you have a version number, a chunk. And it is very important for these chunks. They have also some lead space. So actually, if you submit a new version, and the version is only different only in a chunk, not in the entire data, you save that time. You save submitting new data. Save also disk space. So the configuration and how you retrieve the data. So imagine you have three clusters in 3 different places in the world, and you want to retrieve the data. So you say you have your credential like email, password, and the access token that we gave you when you produce the data. You hit the gateway, and the gateway makes from your credential a user ID and uses also the access token. It goes to the indexing server. By the way, the entire software can run also on a laptop. I mean, when I say indexing server, this means also basically just abstract server. So it goes to the index server, builds the URL, and returns the data. In addition, we have different servers also, the job center that schedules different tasks. And we have also a monitor, cluster monitor, that looks for the health of the hardware, if there is a bit rot, if there are broken disks, and so on. So I'm sure that you'll see this word here in this conference for the first. So why? First of all, you know that Weissman much earlier said that every software company have to build their own hardware. So we always wanted to build hardware, but we had also concrete tasks. Imagine a desert somewhere in Namibia, and in this desert you put an observatory, and these are 4 60 centimeter telescopes with 250 cameras that make an image every 3 seconds, a lot of data. And you want to transmit this data somewhere to the data center. And you use something like this, of a billionaire network. And you're trying, and you're trying, and you're trying, and you get this one. So we thought that's not good. It doesn't work that way. So what we did is we designed our own prototype because we're insane, as I told you. We started with storage pods, and one storage pod is a mini with 16, 20 terabyte disks. And you can see here the characteristics of this installation. Basically, this holds the data for about 1 month. We put them in a rack, and we put the rack in a container. And such a container, this is a very standard transport container, 1/4 container that you use in big ships and trains and so on. And it has a capacity of about 1.4 exabyte and can hold the data for such an observatory for about 4 years. And when you're ready, you get the rack, bring it somewhere to Germany or to US, and put the next rack. And of course, you need airco and so on. And it is very important because it's Namibia. You don't have a power supply. You see here, maximum power supply is 15 kilowatt peak. So we need to make a very good control of the disk power supply. So we use something that Apple, I've heard, and I was scared. It probably is not supported for a long time. It's called core storage. And the core storage is fantastic old framework that not fully implemented with the new APIs. That actually has stuff like we can tell to a disk now wind down or start the disk again and so on. So actually we achieved in our test, we achieved actually to use only 20% of the electricity that is needed for a standard, say, Dell server with the same amount of disk. And this is a big, big plus because we want to have this sign for ours. So the status of our project. I told you that it is very important to have a stable, well-designed APIs. So we decided that we are first going to dogfood our own project. And at the moment we are working in 3 different systems. The first one is, we call it a telescope observer. It will be soon, we'll see it in the App Store. But we have also a special framework and other things that we're open sourcing for describing observatories and also for collaborating between astronomers. So they exchange images and all stuff. Basically a Facebook for astronomers. Then the big challenging project is the Space Junk project, to collect the data from different observatories and to distribute it to universities, to space agents, and so on. And a small pet project just to test our frameworks, and this is for basically a backend for application like the Apple Photos, if you want to submit photos there. In progress, we're replacing small bits of our old software with new software. So our old software is mostly written in Java. Now everything is new stuff is written in Swift. But we cannot make this huge, for instance, file system at once. So we started with stuff like, for instance, C with FS, so that we can start testing our API. We are also playing with different APIs and migrating all stuff and so on. So that we want to see that the system works well with a lot of data existing. And this is where we are at the moment. And we need your help. First of all, if somebody wants to test, if somebody would like to sponsor us so that we also open source parts of this system, or, I mean, we will open source parts of this system, but if you want it faster, because we have also to work for our sandwich. So we will be very happy if we find here a community that would like to work with. As I told you, this project was in work, started about 10 years ago. So many people were involved, and I want to say a thank you to them. First of all is Tommy Engel, probably some of you old-timers know him from Woko, from GNU Step, and so on. Then our telescope partners from Austria, ASE. Rick Hessman, he's from University of Göttingen, who taught us everything about large astronomical. We got the Krupp Foundation sponsored the first robotic observatory software, and my son did, because I have two left hands, about design and so on, and about many ideas. And of course, all my very, very bright, smart, and good colleagues. So thank you for them. If you have questions, you can write me or go to our website. By the way, I have also somewhere produced a small brochure here. I can give you also with this one, especially if you want to see the hardware. Come to me. And I will say thank you for your attention. And I'm happy to answer